All right, Differential Equations, Chapter 8. We're finally getting to this systems of differential equations. So we haven't done any of this, but it has been scattered throughout the book as we've been learning some other things. Every once in a while they throw in a system of differential equations, but I don't think we looked at it at all, really. Listen, so here's the game. The rate I'm looking for two things. I'm looking for x as a function of t, and I'm looking for y as a function of t. So I've got two dependent variables, x and y, that both depend on the independent variable t. So look at this, and they're tied together. They're not just two separate, they're tied together because the rate at which x is changing with respect to t depends on both x and y. The rate at which y is changing with respect to t depends on both x and y. So it's a system of two differential equations with two dependent variables. We're looking for two solutions, x as a function of t and y as a function of t. So we're going to try to use matrices, although there has been some other methods scattered throughout the text. But here we are in Chapter 8, we use matrices. So what we do is we call this matrix, it's a little column matrix, I'm going to call it X prime. Big capital X, big capital letters is a matrix. There's a coefficient matrix called A, there's the coefficients here, times the unknown variables x and y, which is this capital X. So big capital X prime, because that's the derivative with respect to t, AX. In other words, here, let me say it again. This is dx dt, dy dt, written as a little column matrix, equals the coefficient matrix 2, 2, 1, 3, that's my A, multiplied by the unknown variable matrix x, y. So that's this written like this, shorthand is this. So I'm going to try to teach you how to solve this now. Just a little theory here first. Hang on. A little bit of theory here. So let's just go over here. We have this x prime equals ax. Okay, so then again, those are matrices, and there they come from this. But this could be generalized to 3x3s, 4x4 situations. But you know what, boy, you know what that looks like to me? Man, way back, one of our first DEs was y prime equals ky, where we said the rate at which something is proportional to the amount of stuff. We would solve this and we would get this classic exponential growth, exponential model. I mean, this is not matrices, this is just real numbers. But that looks like that. So here's what we do. We assume we know what the answer is. We assume the answer x, big capital X, is some vector called k, that's a constant k, multiplied by e to the lambda t. That's a Greek letter lambda. So this is our assumption. Again, the capital letters are the matrices. E to the lambda t is just a function, e to the lambda t. So we assume that this is the solution, based on some previous knowledge, based on the fact that it's x prime equals a constant matrix A times x. We think it's got this e function involved. So if that is the solution x, then we can sort of plug it in. Let's find x prime. Let's see, can I do the derivative x prime? This k is a constant vector, column matrix vector. So the k is a constant. When you take the derivative of the e to the lambda t, the chain rule spits out a lambda, so I'm going to call this lambda k, e to the kt, lambda k, e to the lambda t. When I take a derivative, I plug it in, and so x prime is this lambda k, e to the lambda t, that's x prime, equals the a times the x, which is k, e to the lambda t. You can divide out those e to the lambda t's. You can divide that out. This lambda is not a vector. I mean, is not a matrix. The lambda is just a scalar number multiplied by a matrix k. I'm going to move it over to the other side, and so I'm going to write A capital K minus this lambda K. And then I'm going to factor out the K out the back end. I can't factor it out the front. And then when you factor the K out, it's gone. There's a capital A there. When you factor the K out the back end, you're left with lambda, which is a scalar. But when you can't do that. So when you factor the K out, you're left with lambda I, the identity matrix I. Because what's I times K? Just K. You're left with a 1, you know? But in matrix language, that's that. All right, K is not 0. K is a non-zero vector matrix. I keep saying matrix, vector. It's a column matrix, which I call a vector sometimes. And so it's non-zero. So then if this is going to be 0, then this has to be 0. And if that's going to be 0, then what we say is that the determinant of this is 0. The determinant of this is 0. So that's what has to happen. And then, so that's the key to this problem. And I tried to kind of give you the theory behind it here. I'm going to erase all that. Most of it, maybe. So this is what I want to do now. I want to set this up, and using this, I can find these lambdas. This is, when we do this, let me give you a couple more notes here. This is called the characteristic equation. This is what we're going to do. And it's called the characteristic equation. And those lambdas, when we find them, they're called eigenvalues. And those, and when we plug them back in, we kind of plug them back in, we find the associated K that goes with each lambda, and that K that goes with each lambda is an eigenvector. So that's where we're headed. And this was sort of some theory here, but this is what I need to do. So it's a determinant, and it's a determinant of what? Of A minus lambda I. Now hopefully you recall what I is. I don't know if I told you. It's 1s down the diagonal. It's 1s down, 0s everywhere else, and 1s down the diagonal. Even if it was 3 by 3 or 4 by 4, 1s down the diagonal, 0s everywhere else is the identity matrix I. So when you multiply by lambda, you get lambda on these diagonals. And then when you subtract it from A, you subtract it from this diagonal. So I'm doing all that kind of in my head. What I get is I get 2 minus lambda. I'm subtracting the lambda from that diagonal. I'm subtracting a 0 from that, so that doesn't change. Same with that 1, but I subtract a 3 minus lambda there. And then I'm setting this equal to 0. So now I do this determinant. This is my A minus lambda I determinant. And I do it. And you know how to do a determinant. You multiply that diagonal. So 2 minus lambda times 3 minus lambda minus this number, this multiplication, this diagonal, minus a 2. Minus a 2 equals 0. We set it equal to 0. All right, I need a little room. This is fun, ain't it? You gotta admit, this is pretty fun. That was the key right there. That's the key. I might erase something important there. Let me see. All right, let's work on this. I'm going to foil it. I'm going to move up here. I'm foiling this out. That's a 6 minus, 6 minus 2 lambda minus 3 lambda. That's minus 5 lambda plus lambda squared minus this 2 equals 0. Hey, it's a quadratic equation. You get lambda squared minus 5 lambda plus 4. Right? I grouped the 6 and the 2 together there, and I just reorganized there, equals 0. Hey, you factor and you found your lambdas. You factor and you find your lambdas. Lambda minus 4, lambda minus 1 equals 0. The lambdas are lambda equals 4 and lambda equals 1. That's awesome. We're getting there. We're almost home. We found lambda equals 4. Those are my eigenvalues. Now, the thing I erased there said a minus lambda I times k equals 0. I had that on the board a little while ago. So in other words, that's true, and this will help me find k. So when I plug this lambda back in here, but don't treat it like a determinant, treat it like a matrix, a minus lambda I. So this is your a minus lambda I, but don't do a determinant. Put the lambda back in there. So for lambda equals 4, a minus lambda I turns into, subtracting lambda 2 minus 4 is a negative 2. That's a 2. That's a 1. And when I subtract a 4, that's a negative 1. And that multiplied by the unknown vector k, which is a k1 and a k2, has to equal 0. So it has to equal 0, 0. So that was a key idea. The a minus lambda I times the k, using that idea, was my next step here. And now, do you remember how to multiply matrices? You multiply this row by this column. Negative 2k1 plus 2k2 equals that 0. You multiply this row by that column. 1k1 minus k2 also equals that 0. And you sort of have a system of two equations, two unknowns, to try to find k1 and k2. Now here's the deal. Always, you won't be able to find k1 and k2 with this system right here because they're always dependent on each other. You notice how negative 2 times this equation is that equation. Negative 2 times this equation is that equation. So these are always dependent on each other, and therefore you can't really solve. So here's what you do. You don't really need both of those equations because they don't work. You just need one. One of them's the same as the other one is what I'm trying to say. And so I'll just go with this top one I had, but the bottom one's a little easier. But I'll just go, and what I get to do is choose, let's see, let me try something here. Let me move this 2k1 over. 2k2 equals 2k1 when you move that over. Maybe you already see what's up. Divide by 2. K2 has to equal K1. So you choose K1 to be whatever you want. I would choose K1 to be a 1. If K1's a 1, then what's K2? K2's a 1. They're non-zero, so they can't be zeros. A 1 and a 1. It could be a 2 and a 2, or a 3 and a 3, or a 4 and a 4. It doesn't matter. It would be a parallel vector if it was. But just pick something easy. 1 and 1. So there we did it. We found the eigenvector that goes with the eigenvalue. Let's do it again. For lambda equals 1, we have to do it again. For lambda equals 1, we plug 1 in on these diagonals here. When we do, we get, when I plug a 1 in here, I get the matrix, wait a minute, 2 minus 1. I get 1, 2. And then I plug in a 1 there, so I get 1, 2. And that's multiplied by the k's, k1, k2, and it has to equal 0, 0. Again, you see it, right? Remember I said there's two equations, two unknowns, but they're dependent system of equations. It's the same damn equation twice. So you really don't need two, you just need one of them. So here's, what is it? 1 times k1 plus 2 times k2 equals 0. So there's a relationship here that you can find the eigenvalue. I would move the k2 over, I guess. K1 is negative 2k2. What if you let k2 be a negative 1? If you let k2 be a negative 1, then what's k1? If k2 is a negative 1, that's positive 2. 2, negative 1. That's the eigenvalue, vector. That's the eigenvector that goes with that eigenvalue. All right, I'm going to to keep going. We're done. I mean, we're finished. We have to figure out how to write our answer. By the way, we just did this example and we got 2 real eigenvalues. Guess what? This process gets a little crazy what if you get a repeated eigenvalue? Or what if you get complex eigenvalues? So there's more to the story. We're not going there. We're going to stick with real eigenvalues. So if you're starting to feel sorry for yourself, like this is tough, I'm trimming away a lot of the tougher stuff. We're going to stick with real eigenvalues, and we get these real eigenvectors, and we have the solution to this DE. Now let's see. Maybe you remember to this system of DEs. Maybe you remember that we assumed the answer to this was a k. There's this k, e to the lambda t. That was the assumption back over there. And so that's one of the solutions. That's called x1. Guess what the other solution is? x2. It's that other eigenvector, 2, -1, times e to the lambda, that's that lambda, t, 1t. There's just t. It's the eigenvector times the e to the eigenvalue times t. So there it is. That's x1 and x2. So what's the general solution, x? Okay, I'm getting rid of this stuff. The general solution, x, is c1 times x1 and c2 times x2. So if I had some initial conditions, I could find c1 and c2. If I had some initial conditions, I could. And so what is this? Remember, this is big capital X. And so what's big capital X? Big capital X is the unknown x and y. So what we have here is x as a function of t and y as a function of t. If I take it out of matrix form, back to a system of we used matrices we transferred this into matrix language. We got the answer in matrix language, but if I go back, if I wanted to, just go back, if I read the top row of this, I have c1 times 1 e to the 4t and 2c2 e to the t. That's the top row. That's x as a function of t. Y as a function of t is the bottom row, c1 e to the 4t minus c2 e to the 4t, e to the t. And that's the 2 functions that satisfy this system of differential equations. Wow. All right. We might try to find an application. Why would you want to do this? What do we want to do? And there's several applications, but the main one I like to think about is this one. There's a tank. But, well, there's 2 tanks. There's tank X and there's tank Y. And maybe we're putting some stuff into X. We're draining X, but when we're draining X, we're putting it into Y. And when we're draining Y, we're putting it into X. So this is a hell of a nice an example of, and especially if we had 3 tanks, then we could do a 3x3 scenario. All right, I guess you're looking forward to the next video. All right, thank you.